Now, I will invite Afees, a postdoc in our group. He will take it from here. Thank you.
Yes, thank you, Umit, for the nice presentation. Most of the research on genetic research on methane emissions have mainly focused on lactating cows. And little or no research have been conducted on non-lactating animals such as bulls or heifers. And as some of us may know, bulls are the main drivers of genetic improvement in dairy cattle farming because, one, the semen from a single bull can be used to inseminate hundreds of thousands of cows, thereby allowing us to spread the good genes that the bull has quickly. Also is the selection intensity, which is the proportion of individuals that become parents of the next generation, which is very high in the bulls. So it helps us to accelerate genetic gain. Therefore, in order to be able to accelerate genetic gain for reduced methane emissions in dairy cattle, there is a need to phenotype bulls, which is the aim of this work. So this work is was conducted with two of the world's leading AI companies, that is ABS Global and Peak Genetics. And what we did was we phenotyped bulls of around 5 to 6 months old for 21 days using GreenFeed system. And because these bulls have no job, we see them visiting the GreenFeed system. So we are able to generate massive amounts of data. So you can see in the image, everybody is waiting for its turn to visit the GreenFeed system, which is a good thing for us. So this is some of the preliminary results we have so far. We have about 220 bulls so far. So it's an ongoing research. And on the y-axis, we have the CH for methane production in grams per day. And on the x-axis, you have the bulls. And this plot is sorted from the lowest average methane production to the highest average production. And we see huge variation in the amount of methane produced by these bulls, which is something that makes us excited as geneticists. And we see that the average methane production is around 130 grams per day. So here we have the plot of the residual methane production. That is methane production adjusted for body weight and average daily gain. And again, on the x-axis, you have the bulls, and on the y-axis, you have the residual methane. And these values ranges from minus 36 grams per day to around 26 grams per day. So when a bull has a negative residual intake, it means based on the bull's body weight and average daily gain, the bulls produce less methane than expected. So these are the environmentally friendly bulls. While those that have positive residual feed intake, positive residual methane production are those that are not environmentally friendly. So here, I'm going to show you one of the interesting results we also found with the limited data we have so far. And on the y-axis, you have methane production, while on the x-axis, you have different production parameters and genetic merits. So in green here, you have the correlation between methane production and body weight and average daily gain. And we see a positive correlation, which is what we expect, that bulls that are fast growing and have higher body weights, they tend to produce more methane due to their physiological structure, bigger rumen that allows much high amount of methane to be produced. While in purple, we see that methane production is positively correlated with the genetic merits of the bull for production traits. So in this instance, we have milk yield, fat yield, and protein yield. What this means is that bulls that tend to produce high amount of methane tend to have daughters that have high milk yield, high fat yield, and high protein yield. These ones in blue or green, you have correlation between methane production and health and fertility traits. And what we notice here is that bulls that produce less amount of grain tend to have daughters that have high productive life and they are fertile. And in red, we have the correlation between methane and feed efficiency traits. And what we see is bulls that produce high amounts of methane are less feed efficient because they have a positive genetic rate for residual feed intake, and they have negative correlation with feed save. So the amount of feed being saved is small. So you see it going in the negative side. Much energy is wasted in terms of methane being produced. So far, we have been able to address some questions, but due to the limited data sets we have, there are still some open questions we're going to address in the coming months. And is how much of this huge variation we see in methane production in bulls is due to genetic factors. And more importantly, we are going to look at the genetic correlation between methane produced from cows and those from bulls. Because if this genetic correlation is high, we can combine both data sets in one training set or one reference population for the prediction of the breeding values. And secondly, if this correlation is high, we can use the information we get from bulls to make selection decisions on cows. So here is just a summary of the current effort of our group. We've talked extensively about the genomic solutions, which is permanent and cumulative. We are also working on microbial solutions as a group, and I'm going to invite you to a talk by Negin that's going to happen in this hall at 2 p.m., which is going to delve into microbial solutions in more detail. Also, we are working on nutritional solutions, and as you know, diet is a main factor, a major contribution to the amount of methane being produced by a cow or a bull, because when you give a bull a diet that is rich in fiber, it tends to produce much higher amount of methane. But due to time constraints, I'm not going to be able to delve deeper into this. And lastly, we're working on a spectral-based solution as a sort of a management tool, because methane is an expensive and difficult trait to measure. So this is the research station in Matfield, and we had 32 preparous cows in the same pen with the same diet. And what we see is huge variation in the amount of methane being produced. And like I said earlier, methane is a very difficult or expensive trait to measure. So not all farmers are going to be able to afford the fancy equipment or those equipment Imut have described earlier to be able to measure the amount of methane being produced by their animals. So it's going to be good that a farmer has a tool to identify animals that are high emitters and those that are low emitters, to be able to have some sort of a targeted management strategy on these high emitters. So do we have the tools to do this? No. We as a group are working on it, which is going to lead me to the result of the study, which we are working on presently. And this is trying to predict methane emissions from cows using farm-level data. So in this scenario, we are trying to use days in milk energy, and metabolic body weight to predict methane. So on the y-axis, you have the predictive correlation, which is the correlation between actual methane being produced and the estimated methane being produced. And we looked at different validation strategies, which is the cow independent, the tri-independent, and the farm independent strategy. And what we see here is that we had the highest predictive correlation from the cow-independent strategy due to the cows in the different folds, the validation folds sharing the same environment. And for the trial-independent and the farm-independent in prediction, we see relatively low prediction accuracy. And this is probably how this, if these were to be used in practice, it's going to be using trial-independent and farm-independent predictions. We're going to try to predict methane emissions from cows from different farms. So what we did now is we added more information into our model using mixed spectral data. And what we see is an huge jump in the predictive correlation. We see almost doubling of the predictive correlation using spectral data. So this showed that spectral data from milk provides added information in terms of predicting methane from cows. And when we added much more information using the genome of the cow, we see no increase in predictive correlation. And this could be due to the spectral data and the genomic data capturing the same source of variation in a data set. Also, we have a pretty small data set so far. So in the coming months, it's when we have much more large data set, it's possible this predictive correlation is going to increase when we had genomic information. So in conclusion, there is growing public and consumer scrutiny over dairy farming in terms of animal welfare, the economic, environmental impacts of dairy farming. We've talked extensively about methane emissions, and also the pharmacological interventions in terms of use of antibiotics. And then genetic selection has been a critical tool, and we believe as geneticists would continue to be a critical tool to improve dairy sustainability, although we may be biased. And also, it's very important to remember that despite being 15 years, almost 15 years in the genomic era, phenotype is still king. It's still very much important to be able to record the traits you want to improve on. And also, any mitigation strategy that will be employed to improve dairy sustainability needs to meet the farmer needs in terms of being cheap and easy to implement. And also, it should meet the consumer demands in terms of providing high and quality protein from happy and healthy cows. But it's not enough for us to be able to measure methane from cows or bulls, or to be able to estimate heritabilities, because if this trait does not have any economic values, the farmer would not want to compromise their profits to improve the sustainability of the dairy sector. So now so I'm going to end with a question, which is, what is the economic value of reducing methane emissions, which I don't have the answer to. So I would like to thank our collaborators and the funders. Especially, I would like to thank the Dairy Innovation Hub, and I'll be happy to take any questions. Thank you for your attention.
Okay, yes. I can get the questions, and the guys will answer the questions, I'm sure.
Thank you for that presentation, everyone. Just a question, in all of this work, and this is great work, how do we account for the environment? Is the environment playing any role in this, and how would you account for it in your methane emission studies?
They are shy. I can go first. Yes, the environment plays a major role. What we do in genetics is we include in the model what we call a cohort effect, that basically it's a group of individuals that are in the same place at the same time under the same diet and the same treatment. So you basically have individuals that are under exactly the same conditions. Could be kind of a blocking factor when you think about the experiment, and basically you rank individuals within that environment. And in that way, we can control for environment, management, a diet, yes.
And to add to what Francisco said, in genetics, we are mainly concerned with the genetic part. That's the part that is passed from parent to offspring, because the environmental part is very difficult to model and it's very difficult to predict. So mostly in genetics, we work with things, the traits that are heritable, that is, traits that can be passed from parent to offspring, so that we can, in the short or the long time, improve the whole population, so that the whole population have favorable genes. So that's when we say it's permanent and it's cumulative. I hope that helps. Yeah.
But it's a very important question, right? Because we are measuring right now in 12 different farms at the same time. So each farm has its own management. They use their own diet. Different lactations, different days in milk. So that's the way that we control for that.
Thank you. I'm curious about, or if you saw any effect of diarrhea on methane production. One of the major problems with calf rearing is the incidence of scours or diarrhea, and I was just curious if that disease eventuality has a effect on methane production.
Yeah, no, that's a great question. So Afees data suggests that bulls that produce less methane tend to have daughters that they have a more productive life, so they are more fertile and more healthy. So based on that data, I would not expect a negative relationship between reduced methane emissions and increased susceptibility to different diseases. Now, our group, and I have a bunch of colleagues there that work in calves too, we are not measuring right now methane emissions on young calves. I'm thinking in the pre-weaning stage. What we are doing with bulls is we are starting between 5 and 6 months.
All right, I have a question. I deal with primarily what comes out of the back end of the cow, not the front end. So I'm just kind of curious, I know it was mentioned on one of the slides, and that wasn't really talked about, but have you looked at all about how the manure emissions might change from these cows that are producing less enteric, but is it possibly affected on the back end? And if you aren't, is there interest in
Right.
that?
No, I will answer that one. That one is a project that is actually led by Ilario Mantovani. It's one of the IDEAS USDA project where we are actually trying to answer the question is what's the relationship between enteric methane and manure methane, right? And the idea is, let's say that they are correlated, right? Cows that produce more methane tend to have manure that produce more methane. That will be a win-win, because through selective breeding, I will be able to reduce enteric methane emissions, and the manure of those cows will produce less methane than the contemporaries. So that will be a win-win. Let's say the correlation is 0. It's fine. So we will reduce enteric methane emissions, right? And then we will develop new tools. I know you work on that to reduce methane emitted by the manure. What if the correlation is negative? We will create a new problem, right? Because we are reducing enteric methane emissions, but we will make the manure to produce more methane. We are working on that. So if next year you guys invite us again, we will show some results. Am I right, Hilario? Good, yeah, good answer.
I have a little bit of a speculative question for you. What kind of research do we still need, or how soon can we expect some form of a methane trait to be published that farmers can actually use to select on farm?
Guys?
I think it has to relate to the economic value of the traits. So if, and I don't have an answer to that, so if there's an economic incentive to select for methane, reduced methane, I think it's going to be included in the breeding program, in the selection, in the breeding goal. But because presently there's no incentive, I don't, unless, though we are seeing some indications that it seems that when bulls produce more methane, they tend to be less fertile or less healthy. Probably that would, that would, in the long run, be an incentive, because it's suggesting that bulls that produce less methane are more healthy. So you might want to have, in the breeding program, you want to include methane just because of the added benefit you get in terms of being, being more productive and also being fertile, but having more higher productive life and being fertile.
And I can a small comment. Also, one of our results shows the correlation between methane and residual feed intakes are 40% the correlation. And this is good for farmers, because if we select for methane against methane, we can also improve feed efficiency. So right now in my hand, this is the best advertisement for methane for farmers.
Yeah, so when we develop and implement a national genetic evaluation for feed efficiency, in fact, UW-Madison was the most important player of that effort, and is still the major contributor of data to the national database. That evaluation was developed with 4,000 cows. So the answer is, we can tell UMIT, go to your office and this afternoon develop the evaluation, and we will have it. The problem that we have is that farming is for profit. It's not a hobby. So the only way that we will have farmers to reduce methane emissions is if they have the incentives to do it, right? So the incentives could come, hopefully in this country we will have positive incentives, right? I dream that Whole Food one day, Nestlé one day will say, farmers, I pay you more for the milk if you show me that you are reducing methane emissions, and we will have the tools. We will have selective breeding and we will have management. Europe is pushing a lot in terms of sustainability using negative incentives, right? I tax your cows, or you do it or you are out of the business. I don't see that coming. But at the end of the day, we need incentives. As soon as we have economic incentives, we can implement the trait in economic selection index, because the way that farmers select animals is based on an economic selection index, trying to identify the animals that are more profitable, selecting at the same time for 50 traits. So I think we are close to do it. We are still trying to find that dollar value. And that's why we are working with the dairy industry to try to find what would be that value.
Francisco, I have two questions in one. So in the same diet, how much is explained by the genetics? The variation is explained by genetics, and how much is explained by the microbiome? And also, how the genetics affects the microbiome in their cows?
Thanks, Daniel. He's one of our experts in genotype by diet interaction. So if you have a question about that, ask Daniel after that. And he's a nutritionist, so I would say that genetics drives almost all the variation. But let me say, so Negin will present some of our results about the microbiome later today. When we think about the host genome or the genome of the cow, the rumen microbiome and methane emission, right? This is a beautiful system. Very simple, right? It's kind of a triangle, but it's very hard to work with because you have that the microbiome can be a predictor, affects methane emissions, but at the same time is a response variable because we do know that the cow has the genetic ability to control part of the composition of the abundance of the rumen microbiome. On average, the rumen microbiome has a heritability of roughly 30% as a whole. When you go bacteria by bacteria, there are some bacteria that are not heritable, so the cow has zero control in terms of the abundance, and some bacteria are highly heritable, that the cow has a tight control of the abundance of that composition, right? So when we think about selective breeding, will be probably a black box, right? We will breed cows that emit less methane than their best friends, and that could be through the better rumen microbiome or should be independent of the rumen. And at the same time, we can try to manipulate that rumen. So rumen manipulation, selective breeding, and the use of feed additive, for example, they are all complementary and kind of additive effects, right? We can implement or use the three of them together.
Okay, let's have a round of applause for our speakers today. So we will have